Download this code from codegive.com, link in the description below. Big O Algorithm Complexity, a comprehensive tutorial. Understanding Big O notation is crucial for any programmer, especially when working with algorithms and data structures. It provides a standardized way to analyze and compare the efficiency of different algorithms, regardless of the specific hardware or programming language used. This tutorial will delve into the common Big O complexities, explain their implications, and provide illustrative code examples in Python. What is Big O notation? Big O notation describes the upper bound of an algorithm's runtime or space requirements as the input size, n, grows infinitely large. It focuses on the dominant factors affecting performance, ignoring constant factors and smaller terms. We're interested in the order of growth, not the precise execution time. For example, an algorithm with O, n superscript 2, will generally be slower than one with O, n log n, for large input sizes, even if the O, n superscript 2, algorithm might be faster for very small inputs. Common Big O complexities *. We'll examine several key complexities, arranged roughly in ascending order of inefficiency. 1. Constant time *. The algorithm's runtime remains constant regardless of the input size. Access to an element in an array using its index is a classic example. 2. Log n, logarithmic time *. The runtime increases logarithmically with the input size. This often occurs in algorithms that repeatedly divide the problem size in half, such as binary search. 3. N, linear time *. The runtime increases linearly with the input size. Iterating through an array or linked list once is a typical example. 4. N log n, linearithmic time *. A combination of linear and logarithmic time. Efficient sorting algorithms like merge sort and heap sort exhibit this complexity. 5. N superscript 2, quadratic time *. The runtime increases quadratically with the input size. This often happens in nested loops where the inner loop iterates through the entire input for each iteration of the outer loop. Bubble sort and selection sort are examples. 6. 2. Exponential time *. The runtime doubles with each addition to the input size. Algorithms that explore all possible subsets or permutations often have exponential complexity. Recursive Fibonacci without memoization is a classic example. 7. N. Factorial time *. The runtime is proportional to the factorial of the input size. This is the worst-case complexity and arises in problems requiring exploration of all possible permutations, like the traveling salesperson problem. Space complexity, Big O space. Big O notation also applies to space complexity, which measures the amount of memory an algorithm uses as the input size grows. The same complexities, O, 1, O, n, O, and superscript 2, etc., apply. For example, *O, 1 using a fixed number of variables, regardless of input size. *O, and creating an array of the same size as the input. *O, and superscript 2 creating a 2D array with dimensions proportional to the input size. Choosing the right algorithm *. When selecting an algorithm, strive for the lowest possible Big O complexity, especially for large data sets. A small difference in Big O can significantly impact performance. O, n log n, is generally considered very efficient, while O, n superscript 2, or worse can be problematic for large inputs. Conclusion *. This tutorial provided a comprehensive overview of Big O notation and its practical applications. By understanding these complexities, you can make informed decisions about algorithm selection, optimize your code for better performance, and write more efficient programs that scale effectively. Remember to always analyze the worst-case scenario when determining the big O complexity of your algorithms. While specific runtimes can vary based on hardware and implementation details, the big O notation provides a valuable comparative measure of algorithmic efficiency.